Hello everyone, welcome back. Let us continue our discussion. We are in week 7 and this is our second lecture. If you recall, in the previous lecture, we started our discussion on bending stress. And its distribution, right? Today, let us continue our discussion with an example. So we start with a simply supported beam. Its length is 9 meters and it is partly loaded with a UDL. The loaded length of the beam is 4 meters and the intensity of the UDL is 1800 kg per meter. Our task is to find out maximum bending moment and the bending stress distribution at the location where we have maximum bending moment given the depth of the beam, which is 0.3 meter, and moment of inertia is 231 into 10 to the power minus 5 meter to the power 4. So let us solve the first part. Two ends of the beam will have reactions. So the left end is say A, the reaction is RA. Similarly, at the right end, we have RB. Now if we consider all the forces causing moment and the moments about the point A and taking anticlockwise positive, which is equal to 0, that's the moment equilibrium equation. So we have RB times length, which is 9, and this force is positive, minus we have 4 times 1800, that is the force multiplied by the lever arm, which is 2, and this moment is negative as per our sign convention. So we can solve this equation and what we get is the reaction RB, which is 1600 kg. Right. Now we can find out RA, which is the total applied load, that is 4 times 1800 minus 1600, and the value is 5600 kg. So we have 5600 and 1600. Now, if we consider a section at a distance, say x from the left end, then the shear force Vx we can estimate at this section, it is Ra. So what we do, we consider all the forces on the left side of this section at x, and if you recall the sign conventions, left up, right down, so Ra is positive, minus we have x times 1800, right? Obviously, if you put x equal to 0, we have Vx, which is equal to Ra, and that is 5600. So At this end, we have 5600. Then, as we progress along the length of the beam, Vx, which is the shear force, it reduces linearly, and at x equal to 4, we have Ra, which is 5600 minus 4 times 1800, and this is equal to minus 1600, right? So here at this point we have 1600, and in between the shear force diagram linearly varies. So this is basically the point where shear force is 0. That will solve in a minute, but as we progress beyond 4, this value will remain constant, and at the extreme end when it comes, we'll again have 1600 here. So this triangular part is positive, and here we have negative. Okay, so now the first task is to find out the distance from the left end where we have shear force 0. So for that, what we do, we put Vx equal to 0, and if we do that, we get x is equal to Ra, which is 5600 divided by 1800, and the distance is 3.11. So this distance from the left end is 3.11 meter, where shear force is 0. And you know, the location where we have shear force 0 is where the bending moment is maximum. So effectively what we have to do, we have to find out the bending moment at x equal to 3.11 meter from the left end. So that we'll do in a minute. So we again consider the section at x, and then at that section we find out what is the value of bending moment at that particular section, that is mx, and then we vary x to find out the variation of bending moment along the length of the beam, right? So mx is equal to Ra times x, as per our nomenclature, this is negative, plus we have x times 1800 times x by 2. So effectively what we have, 900 x minus Ra, which is 5600, sorry, 900 x square minus 5600 x. Okay. Now in this equation, if you put x equal to 0, you get bending moment 0, which is at the left end, right? Because we have simply supports at the two ends, we have bending moment 0, right? So at the two ends, bending moment 0, and in between, we also have the variation. So at x equal to 3.11 meter, let us find out what is mx, and that is 900 times 3.11 square minus 5600 times 3.11. Okay, so let us calculate that. It is minus 8711.11 kg meter. Now, so what we do, we start from 0, and when we come to the location where we have 0 shear force, there we have the maximum bending moment, say here. So let us also find out when x equal to 4, mx is so we have minus 1000 kg. So it is somewhere here. Now between this, we have quadratic variation of bending moment. And then as we move along, the length of the beam will have linear variation, which ultimately leads to 0 at the other end. So this is sagging, and we have our EMD. So the maximum bending moment we have estimated, and we have to find out the bending stress distribution given the depth of the beam and the moment of inertia. So now we are in the second part of the problem. Okay, so maximum bending moment is 8711.11 kg meter. And if you recall, we derived sigma by y is equal to m by I. Right? So sigma is equal to applied bending moment. In our case, it is 8711.11 divided by 231 into 10 to the power minus 5 into y, that is the distance of the extreme fiber norma from the neutral axis. So depth of the beam is 0.3 divided by 2 is basically the distance of the extreme fiber. Okay. So now what we have effectively is 0.15 times 8711.1 divided by 231.0 into 10 to the power minus 5. Okay. And if you evaluate this, you get 5.66 into 10 to the power plus 5. Right. So this is in kg per meter square. Fine. So the stress at the extreme fiber sigma is equal to 56.6 into 10 to the power 5 Newton per meter square. Right? So that means we have 5.66 MPa. Right? Okay. So now we have the maximum bending stress, and we already know it varies linearly over the length of the beam cross section, and let us draw that. So we have a rectangular cross section, and the depth is 0.3 meter. So over this cross section, we have to draw the stress distribution, which is linear. And because it has a sagging moment, the expected deflection is like this only. So we'll have compression at the top and tension at the bottom. So if we join them with a straight line, we get the bending stress distribution, right? Okay. So let us join it. So compression is negative, tension is positive, and the value is 5.66. So that's the bending stress distribution for the applied load over the beam, right? Okay. Let us take a different example. So our example 2, and we have a cantilever beam. Let us see how their applied bending moment varies, and then how we can find out the bending stress distribution. So this is 700 kg, and we have triangular pattern of the applied load. The length of the beam is 5 meter. So say this is A and B, and for this beam we will find out the bending stress distribution at the middle of the beam. So find sigma max at the rate 2.5 meter. That means at the middle. Okay. What is given? Depth of the beam D is 0.2 meter, and the moment of inertia I is equal to 1.76 into 10 to the power minus 3 meter. Okay, for this problem we have to find out moment mx for x equal to 2.5, right? So which is somewhere at the middle, right? Now what will be the intensity of the load at this point? It is obviously half of this load, so this is 350, right? Okay, now what we can do, we can split this load on the right hand side. So instead of solving the complete problem, let us come from the right hand side, because in this problem we are not going to draw the shear force bending moment diagram. Just we have to find out the maximum bending moment and respective bending stress distribution. Okay, and the location of that bending moment is given at x equal to 2.5. Okay, so let us come from the right hand side for this problem, and at this location we have two forces acting. You can see we have a rectangular part of the load plus a triangular part of the load, and that we can take separately and add the effect caused by these two forces. Okay, so now the first part 350 and times 2.5, that is the length of the beam, and the CG of this load is somewhere middle, so 2.5 by 2, effectively that is the moment caused by the rectangular part of the force. Now for the triangular part we have half times 2.5 times the load intensity, half of the load intensity at the right end, so again it is 350, and then we have the location of the CG, which is somewhere here. So we have 2.5 minus 1/3 of 2.5. Right? So from this end, it is 1/3 of 2.5, Okay. So 350 times 2.5 square divided by 2, which is 1093.75, plus for this part we have 729.16. So the total is 1822.91 kg. Now sigma divided by y is equal to applied bending moment divided by I, right? So what we have, sigma is equal to applied bending moment, that is 182291 times y. Our depth is 0.2 meter, so half of that, it is 0.1, and then 1.76 into 10 to the power minus 3. Okay. So we have kg per meter square, right? And again, let us draw bending moment distribution, sorry, the bending stress distribution across the section. This is the neutral axis, and then because it is a hogging moment, expected deformation is slope is 0 at this end. So we'll have tension at the top. So that means tension we consider positive. So tension at the top and then compression at the bottom. This is minus, plus, and the value of this is right. So now we see how we can plot the bending stress distribution across the section, right? Okay. So let us continue our discussion. So the expression we have derived is m by I is equal to sigma by y. Y is the distance of the extreme fiber normal from the neutral axis, is equal to E by R, right? Now sigma is equal to m times y divided by I, right? Now if we modify this equation, we have m divided by I by y. Now when we have y equal to y max, then I divided by y max is called z, that is section modulus. For a given section, we can find out this section modulus for the extreme fiber, and then sigma max is equal to m by z, right? So if you have a particular section, for that we can find out this section modulus, and the section modulus is nothing but the moment of inertia divided by the distance of the extreme fiber from the neutral axis, right? Okay. So now let us again take an example. So we have a steel plate and the dimension of the steel plate is given. It is 20 centimeter and the depth is 4 centimeter. So the steel plate is bent into circular arc of radius 15 meter. So find the maximum stress induced given E is equal to 2 into 10 to the power 6 kg per. So sigma by y is equal to m by I is equal to E by R, right? So effectively what we have, sigma is equal to E times y divided by R. So E is 2 into 10 to the power 6 times y, which is the depth divided by 2. So that is 2 centimeter divided by R, which is 15 into 100. And if we solve this, we get 26.67 into 10 to the power 2 kg per centimeter square. Now we can also find out I for this section, which is 1 by 12, 20 times 4 cube. So this is equal to 106.67 centimeter to the power 4. So you can also estimate the applied moment. M is equal to E by R times I. So what we have, 106.67 into 2 into 10 to the power 6 divided by R, which is 15 into. Then if we solve this, we get 14.22 into 10 to the power 4 kg centimeter. Okay, so you can see how we can find out the section modulus and use that to find out the bending stress distribution across the section. Okay. Now let us evaluate section modulus for some standard sections, right? So let us see the expression of section modulus for, say, a rectangular section. So we start with a very simple rectangular cross sections. So the width is B and the depth of the beam is D. For this beam, moment of inertia is 1 by 12 B D cube, and neutral axis is at the middle of the beam. So Ym, that is the distance of the extreme fiber from the neutral axis. So here is the neutral axis. So this is D by 2. So Ym is equal to D by 2. And if we use these two, we get Z which is equal to I, that is the moment of inertia, divided by Ym. So we have 1 by 12 B dq times 2 by d. So that means we have 1/6 B d square. So that's the section modulus for a rectangular section. Now, instead of section modulus of a rectangular section, we consider a hollow section. Let us see how it changes from a solid section to a hollow section. So this is a B and the smaller one. So this is small b. Similarly, the total depth is capital D and depth of the hollow part is small d. Then we can again find out moment of inertia. For the bigger one, we have 1 by 12 B d cube minus we have 1 by 12 small b small d cube, right? And Ym is the distance again from the neutral axis to the extreme fiber. So this is capital D by 2, right? Okay. So now Z is equal to 1 by 12 BD cube minus small b small d cube into 2 by d. So we have 1/6 BD cube minus small b small d cube divided by capital D. That's the expression of the section modulus if we have a hollow rectangular section. Now, if we have a hollow circular section, then let us see how the section modulus varies. Okay, so the bigger one again, we have the diameter capital D, and the smaller one we have diameter small d. Again, neutral axis is at the middle, and the distance of the extreme fiber is capital D by 2. So the moment of inertia of this section is pi by 64 times d to the power 4 minus small d2, right? And y max is equal to d by 2. So what we get, z is equal to pi by 64 capital D to the power 4 minus small d to the power 4 times 2 by d. So we have pi by 32 capital D to the power 4 minus small d to the power 4 divided by. So that's the expression of section modulus for a hollow circular section. Similarly, if you have any other geometry, you can easily find out the section modulus, and once you find out section modulus, using that information, you can actually find out the bending stress distribution. So let us take the last example for today's discussion. So we have, say, a simply supported beam again, and In this case, we have a point load at the middle, which is 75 kg. And the length of the beam is 1 meter. The cross section of the beam is given, which is rectangular, and the width of this cross section is 2 centimeter by 4 centimeter. Obviously, neutral axis is at the middle, and the distance of the extreme fiber from the neutral axis is 2 centimeter, right? Now the question is, what is UDL required for cantilever beam of 2 meter and with cross section of 5 centimeter into 10 centimeter. That will produce the same level of stress, right? So for this, we find out what is the maximum stress that occurs at the middle. So MC, say central value of the bending moment, MC is equal to W, which is the load acting at the middle, times L by 4 is the applied bending moment at the middle, right? Now, we have load as 75 kg times length of the beam is 100 kg, 100 centimeter divided by 4, and we have 1875 kg centimeter. Okay. Now, for this MC, we have the bending stress is 1/6 B d square times sigma. So if you recall, for this rectangular cross section, we have the Z as 1/6 B d square, and M by Z is sigma. So we have this expression, and we can equate this right hand side with the applied moment. So 1875 is equal to 1 by 6. B we have 2 and D is 4 centimeters. So 4 square times sigma. So what we get, the value of sigma is 351 kg per centimeter square. Okay. Now we'll focus on the question. So we have a cantilever beam of length 2 meter and the cross section is also given. For this cantilever beam, we have to find out the effective UDL. So the problem is, if we have this cantilever beam, what is the effective UDL that will produce? So this is omega kg per centimeter, that will produce the same level of stress at the end. So the stress level we have already evaluated for this simply supported beam at the middle, and then we apply the same stress level and find out what is the effective UDL. Okay. So the length of this beam is 200 centimeter and the cross section is given. Now M at this point we can actually find out. So that M is what we have here. So this is the M, and this M is equal to, we have omega times the length of the beam times the lever arm, which is half the length, and this is 100. Okay. It is in kg centimeter, right? Now, this applied moment, which is 2 times 10 to the power 4 omega, is equal to 1 by 6 B, which is for the cantilever beam 5 times d square 10 square times we have 351, right? That's the applied stress. So we have to find out what is the value of omega. And if you do that, the value of omega is 1.46 kg per centimeter. So we get the intensity of the UDL that is applied over the cantilever beam, which will produce the same level of stress as we can see from this simply supported beam with a point load at the middle. And here you can see how we can use the section modulus to find out the stress from the applied moment, and then we can also find out the distribution of the moment across the section, which for a rectangular section it is linearly varying, and we can plot and we can identify, depending upon the type of bending, whether the top fiber is in tension or compression, and similarly also for the bottom fiber. Okay, so let us close here. In our next class, we'll continue on this topic and we'll see how we can consider a built-up section, and for built-up section, how we can estimate the section modulus, and also we can quantify the bending stress distribution. So we'll meet again in the next class. Thank you very much.